So this is a compound interest problem that is compounded continuously. Now, being that it is compounded continuously, we have a formula named, or mainly like this. Now this is what we would call a first order ordinary differential equation, which can be separated by variables. So now to start this off, we would like to put our sides, or our s's on the left side and our r's on the right side. So basically we're separating them. So let's start off with s prime over t. Of course, we're going to put s over t here since we're going to switch this to this side, so it's by division. And then also we can rewrite this equation as 1 over st times the s prime of t is equivalent to r. Alright, so next we would like to differentiate them, the left side with respect to s and the right side with respect to t. So once we differentiate it, we can write it as 1 over st ds t is equivalent to r dt. Yeah, there we go. Alright, now once we have differentiated them, we would like to integrate them. So we would integrate them on the left side, and what we do on the left side is what we're also going to do to the right side. So let's start off by integrating the smaller one, so r dt, which is because it's easier. So the integral of r dt is only equivalent to rt plus c. Alright, let's put c1 because we're also going to integrate the second one, which is integral of 1 over st ds t. Fairly we can skipping all the parts. This will equate to the ln of st plus c2. Don't forget the c's, because since you are integrating, you must always put the constant at the end. So yeah, now we have both integrated parts. So let's combine them both. That is going to be the ln of st plus c2 is equivalent to rt plus c1. Now what we are going to do here is that we are going to combine both the c's. So we're going to transfer c2 to c1. Since they are both constants, you can eliminate them and just include one c, or one constant. So here we can rewrite this as ln st is equivalent to rt plus c1. Alright, so we're nearing the end of this differential equation. So what we're going to do now is that since we have this, we are going to isolate s of t. So s of t, basically that's going to be ln s of t is going to be equivalent to the logarithmic of e raised to rt plus c1. So now what we're going to do is we can actually disregard c1 since we won't have any constants for the given problem. So now we are going to be left with the differential equation of st is equivalent to e raised to rt. And there we have it. That is going to be our differential equation, which we are going to be using for our compound interest problem. So also I forgot to mention that we are given the condition here that s of 0 is equivalent to s sub 0. So this will be a crucial role, as this will be the amount or the basic amount that is being length or the maximum amount, basically, for our compound interest problem. So for the problem, it states that Bob places $9,000 in a savings account. So it's given that our S sub O is going to be equivalent to 9,000. Next, he pays it 5% interest per annum, which is compounded continuously. So it's given that our rate is 0.05. So what we're trying to find now is the amount of the account after 5 years. So our time is going to be equal to 5. So it's pretty straightforward now that we have all of the values. So we can just substitute in. So it's going to be 9,000 times e raised to rt, which is equivalent to 9,000 e raised to 0.05 times 5. That will be equivalent to, let's calculate, 9,000, where is it, e raised to 0.05 times 5. That's going to be 1,156 times 10 to the negative 3, right? 1, 2, 3, yeah. So that's going to be 1.156. Yeah. So that's going to be our final answer. So that's the rate, or the return. That's going to be the return for the bank account. So basically, yeah. Now to put this to the test, I have gathered a MATLAB equation or a MATLAB code, which is very simple, which uses the ODE45 equation, which I learned through MATLABs using ODE45 to solve an interest rate problem. Now, by pressing enter, wait for a second, there we go. So we are going to have, see, our t is going to be compounded continuously until it reaches 5 years. There we go. Now, since 5 is the last, we are going to go straight down to the last part, and voila, 1.1556. Oh, forgive me, I forgot to write 5 here. There we go. So it's 1.556, which is also what shows on the MATLAB. So that's how you solve a compound interest problem by separable equations with the help of MATLAB. Thanks for watching.
This type of first-order differential equation we will be solving with linear equations. In this section, we will solve linear first-order differential equations in the form y prime plus p of t times y is equal to g of t. We give an in-depth overview of the process used to solve this type of differential equation, as well as a derivation of the formula needed for the integrating factor used. Since we are dealing with interest, our working equation will be ds over dt minus the rate times s is equal to 0. Since our equation takes in the form of linear equation, our integrating factor will be mu of t is equal to e raised to the integral of p of t dt plus c. Thus, we get the solution mu of t is equal to e raised to negative rt plus c. The solution we will come up dealing with linear equation will be y of t is equal to the integral of mu of t times g of t dt plus c all over mu of t. we will be getting the equation 9,000 times e raised to 0.05 times 5. With all this, we will be getting the amount of 11,556.22875. For the MATLAB solution of this linear equation, the user will be asked to input the initial money placed in the account as well as the rate of interest. Now, after pressing enter, the solution will be shown as follows. For this solution, we will be using $9,000 as the initial money placed in the account as well as the 5% interest compound. Now, as you can see, the MATLAB solution and the manual solution are quite similar now. If we substitute 5 to the equation in the MATLAB, we will be getting the exact same answer as the one we solved manually.
So for our problem, Bob places $9,000 in a saving account which pays 5% per annum, compounded continuously. Find the amount in the account after 5 years. The equation that will be used in solving this problem is the Laplace method. The equation will be P of R is equals to the integral of 0 to infinity times f of t multiplied to e raised to negative rt. Given that f is the continuous cash flow function, wherein in the problem f is denoted as $9,000, while r is the nominal interest rate wherein r is equals to ln 1 plus I. I is the rate wherein it is 5% per annum, and t is the time, wherein in the problem t is denoted as 5 years.
In this MATLAB, we have a user interface that asks for the user to input his or her money deposited, the annual interest rate, and the time in years. It then computes for the amount in the account after a given time. For this problem, we have $9,000 deposited with an annual rate of 5% or 0.05 in decimal form, and the amount of years, which is 5 years. Now the program outputs the amount expected after 5 years, which gives a value of $11,486. The same result was obtained in our manual solving. First, we used the formula for compound interest, which is A equals P times 1 plus R over N to the power of N times T. A being the amount, P being the principal value, 1, R equals the annual rate, N is the number of times the amount was compounded, and T is the number of years. Then we plugged in the given values of 9,000, 5%, 1 since it is per year, and T equals to 5 years. After plugging the given values, we have 9,000 times 1 plus 0.05 over 1 to the power of 1 times 5. We then get the value of 11,486.53. To round this up, Bob will have around $11,500 in his account after 5 years.